said it on but I knew that.
All right, so returning to a question, so given some data, our aim is to identify an element G of our class of functions H with the property that the error that it attains for this particular P is less than an optimum, maybe plus some slack, plus some epsilon. And this optimum that is going to be defined to be just the best that we can possibly do. So, so we consider here the infimum for all elements in this class H of the error for that particular distribution P. So infimum, the smallest possible value, the best that we can possibly do for this function class H, we're going to call it opt sub P of H. And what we want is somehow at the end of our work to end up having a function G that is close to optimal. So not worse than epsilon, not more than epsilon worse than the best possible function in the class H. Okay. And so we can try and formalize this as follows. This is the definition now of maybe a formal definition of a learning algorithm. We're going to here suppose that we have a class H that maps from some x to 0, 1. We are in the setting of binary classification. Then a learning algorithm L for the class H is a function of this sort. So L maps from samples to functions in H. An example, we map it to a hypothesis function such that for any epsilon and delta, we can find, or there exists an M naught that is a function of epsilon and delta. It's going to be a number of data points, the size of the sample, with this property. Property is that the error of this hypothesis that the algorithm returns to us is within epsilon of the optimum value. So that's an event, and that event is going to happen with a probability that is at least 1 minus delta. Right.
This is purely mathematical statement, nothing to do with machine learning, right?
This is a mathematical, it's a definition.
Mathematical definition.
It's a definition, yes. If it has to do with machine learning, that's an excellent question. So we're trying to formalize what it means to do learning. So in a mathematical sense, in a statistical sense. And well, that's important if we want to be able to say that we're doing machine learning. So in what sense are we doing machine learning? In what sense can we obtain guarantees for machine learning? Or in what sense can we, come up with a quality criteria or say, we succeeded? What are the limitations of the theory that we're building?
That's the topic of the workshop, mathematics of machine learning. That's the mathematics part.
Yeah, that's true. That's true. No, but I mean, the reason I mentioned this is because there has been quite a bit of debate about what learning means and in contemporary times. Yeah. And there has been quite a bit of, let's say, revisiting of classical concepts of learning and discussion of whether we have to update them, how we should update them, how we should refine them. And because so we're talking here about probability distributions, about expectations, but the same things happen even if you're doing just basic probability. What is a probability? And as a matter of fact, maybe this question doesn't even have a correct answer. But you may come up with a mathematical framework that is consistent, and no matter what your interpretation is, will allow you to produce results. And we're trying to do something like that for the case of learning. Right. So okay, but for the intuition here, the way I like to think about this is that this is going to be kind of a good situation or a good event. A good event being we apply this function L to the sample to this data, and when we evaluate the error, that's going to be close to optimum. So that's the good thing happening. So the good thing happening, we want that this is happening with high probability. So therefore, quality of that should be at least 1 minus delta. All right. So, but we cannot really hope that this will always be true because, let's say I just gave you for the data set a single customer. You looked at a single customer, and how are you supposed to be able to tell with high probability in future something? So this is only going to be possible if the sample that you were using was sufficiently large. And it has to be sufficiently large as a function of epsilon and delta. How close do you want to be to the optimum, and how high is the probability supposed to be? So therefore, what we're requiring here is the existence of a function m naught, a function of epsilon and delta, such that the good event happens, with this specified probability.
So is it true to think that machines, that comes in when we have huge data, because humans cannot process them? The machines, that's their place. I'm very simplistic approach I have.
That's
I'm
great.
a mathematician, not a
No, of course.
scientist.
Yeah, correct. I mean, so as we would see, depending on what you are assuming. So what are you going to? We're going to try to formulate a theorem, right? So for such a theorem, there are going to be premises, and based on those premises, we can make an optimal statement. And the same is going to be mathematically optimal, regardless of whether you are using a machine or a human, right? So indeed, to what extent you can instantiate an algorithm with a machine or with a human brain, that there are differences between the two things. And currently, machines do require bigger samples than humans for some tasks, or at least it seems to us, naively, that that might be the case. May not necessarily be like that after all, because I'm divagating a little, but you could argue that your human brain has evolved through time and has already used a lot of data. And and we also have so in that way. So we're not really learning from scratch, and we're asking machines to learn from scratch a lot of stuff. And maybe it's not a really fair comparison in that way. Also, it depends on what kind of task we're looking at. Maybe at some other tasks, but they are much faster than people in terms of the number of data that they need to discover content. Actually, that's what we're trying to help in some of this. In some problems, maybe we're, for example, in mathematics, it's not only that machines can process a lot of examples, but maybe they really have some other perspectives. Right. So, but anyway, so the hope is that this good situation will kick in and will happen whenever n is larger than this bound m naught. So somehow there exists this function, and if we have a sample that is bigger than this, then this high probability of the good event will be guaranteed. Now, this is at this point just a definition. I haven't said anything about how are we going to construct this algorithm, this mapping from samples to hypothesis functions, or what this function might end up being and not. Could be humongous, could be enormous, could be that it's irrealistically or unfeasibly large. But the point is that as soon as such a function exists, we could at least tell that provided we get a sufficiently large amount of data, we can be as good as we want and with as high a probability as we want. Maybe in some cases you don't really need that this can be arbitrarily large. Maybe you will be satisfied whenever delta can be made as small as 0.1. So maybe 90% probability, okay, I'm happy, and then you will be happy, but formally we take this definition. Yeah.
So it seems like you need the samples itself need to be drawn, I guess, implicitly independently most of the time in these settings, right? Are there other big frameworks people use? Like, I guess you could start something like exchangeability for independence, but if you're then going further to other applications like, I don't know, time series or something, and a lot of these ideas of either independence or exchangeability maybe break down. Are there like similar frameworks for studying those types of problems, or do you study like sequences and you consider that sequence is independent and you get multiple sequences?
To some degree there are, yes, but by far the best understood is the case of independent and identically distributed data. So, I mean, as soon as, for example, your data is not identically distributed, then maybe you're going to be talking about other things, especially when at test time, because we're evaluating here an error, which is kind of test error. So if there is a shift of the distribution at that point, maybe you're gonna say, all right, so this is the out of distribution generalization. Or if your data was not independent, you need to argue to what extent you're gonna have some low Blush numbers kicking in. So you need to be able to satisfy those conditions. We're gonna see a little bit of the structure of the proofs, and you will see how some of them can be extended. But for sure, the best understood setting is when they are independent. Exchangeability is a good pointer. Yeah. So I mean, there are certain lines of generalization results for the setting of sequential decision making. So we will see some of those like regret bounds, things like that, where you're not necessarily assuming that that the data is being observed independently. Or also in the context of active learning, where maybe you're trying to collect the samples, the observations, the examples that we're looking at, you're trying to actively steer and guide how to pick them.
The best sample ultimately from the distribution.
Right. So maybe you observe some customers and you determine that actually if I wanted to have a good hypothesis function, I should go and collect data of that type in order to inform myself about things that I'm not very sure about yet. So you can do that actively, and there's a different setting still, because it could allow you to drastically reduce the number of the sample complexity, the size of the sample that you need to ensure that you're going to be able to do well. All right, so here we're going to talk about the sample complexity of an algorithm L as being this function m sub L, which is the minimum such n that will ensure that we get epsilon delta learning with the class H on a particular algorithm. So this m naught that I showed you before, that would be kind of one possible bound for the algorithm L. And if you say, let me pick the best possible function for this algorithm L, we would call that m sub L. What is the smallest sample size that will give you this nice guarantee? Then we can also talk about an inherent sample complexity for learning with this class H to be the minimum of all possible learning algorithms. So this mapping L as a learning algorithm, maybe it's not the only one, it could be other ones. We already had an example here where several people came up with different hypotheses. You could say they are different learners, different learning algorithms. And, but maybe we had the same, well, maybe they didn't share the same class of functions potentially, but if we fix the class of functions, then we could also look at what is the best that we can do across all the different learning algorithms. All right, so then again, our hope is to produce a function H in the class that has near minimal error, but we don't know what are the actual errors, and so all we know is the data. So therefore, it is natural for us to say, let's try and use the sample errors as estimates in place of the actual error to try and construct the learning algorithm, this function L. Then, so we can come up with a learning algorithm that is going to do the following. For a given data C, it will choose the function that satisfies this condition. So the condition is going to be that, so whatever the output of L is for a sample C is that when you evaluate the sample error of that, that's going to be the minimum among all the possible sample errors that you could get. So in other words, what we're doing is that if we fix the class of functions, the neural network, and now we're going to pick one of the functions that can be represented by the neural network, such that it attains the lowest possible sample error. Minimize the training error. That's one approach to select a function in the class. Is this a good idea? Yes or no? Of course, we sort of assume that it is a good idea, but we need to be sure. Okay, so why this could be a good idea? So maybe concentration inequalities. So first, the notion that the sample error is going to be somehow a good way to start to try to think about the actual error. And there are several concentration results and laws of large numbers, and Hoeffding inequality is a form of statement like that. I have put it here in case you have not seen that. So it is a comparison between a sample mean and an actual mean. It's going to say, so you take a sample, evaluate the mean of that sample, and ask how far is that from the actual sample, from the actual mean. And what it says is that the probability that this difference is too big is very small. So the bigger the difference, the smaller the probability. And this probability drops very rapidly with the size of the sample. So the statement is down here. So here S, S is the sum of a list of independent random variables. So x1 dot 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 xm. And we compare that with the actual expectation value of such a sum. Then the probability that this is bigger than t is going to be less than or equal to exponential of some negative t squared. So it drops exponentially here with t squared in the size of this error. But also we have sitting here something that goes with m. It is not super obvious from the way it is written, but maybe we can take a look at the one here upstairs, which is easier. So for the sample error, you can think of that really as being a sample mean. And for the actual error, just think about it as being a mean. So it's the mean for the random variable b. The random variable takes value 1 if your hypothesis disagrees with the actual label. Takes value 0 if it agrees. So you're not making a mistake and you're just evaluating the expectation value of that random variable. That's the definition of the error. And the sample mean is just the sample error. And so the probability that this difference is bigger than epsilon is at most e to the negative epsilon squared times m. So it drops exponentially with m to the sample size and exponentially with the square of the gap. So that looks pretty good, pretty great. So it seems that with a very small sample already, we can be sure that we're going to be very close to the actual mean, so we can estimate the error. And one of the very nice things about Hoeffding inequality is that, so this is a statement that is valid irrespective of what is the probability distribution P. And this is valuable because we're sort of presuming that we don't know what it is. Maybe if for a particular probability distribution, you could obtain maybe a tighter statement like this, but if you don't know anything about it, so this is pretty nice. So the right-hand side does not depend on P. It just depends on the sample size and this epsilon. Yes? Oh, I thought you had fun. All right, so then, are we done? Is this sufficient to allow us to pick a hypothesis or to allow us to ensure that minimizing the sample error is a good idea? Not quite, and this bound is pretty good if you are looking at a single hypothesis. So we're comparing a single sample mean, and we're basically saying the sample mean for a single hypothesis is close to the actual mean or to the actual error of the hypothesis with high probability. That does not tell us that the sample error of multiple hypotheses are all of them close to the actual errors. And that's a problem because when we're learning, we're trying to select one hypothesis out of several possible ones, and could be that by pure chance, one of them is going to seem to be doing great in the training data, but in reality, it's not doing well, just because you have many of them that you are comparing. So, but if we have a finite set of hypotheses that we're dealing with, we can take a union bound. So, like the probability that any of the hypotheses is doing bad. So, and, you can evaluate the probability that the maximum of this discrepancy is bigger than epsilon. And we can bound that from above just by adding that we have for each of the individual statements. So this is a union bound. And in that case, we would get this sort of statement. This still looks pretty good because we are multiplying here by the number of events that we're evaluating or for which we're taking the union bound. And here we still have the exponential decay, which is pretty good. Or this is going to work so long as maybe this h is not huge. If this h starts becoming very large, or is very, very large, then maybe that's going to signify that, that this is not enough. But if h happens to have a finite cardinality, then this would work. So because this doesn't matter, it's just a constant at the top. Yeah.
How likely is it that the function class would be finite, a finite size, right? It seems like a function class, I think of countably infinitely, many could fit in, just depending on that choice of parameter.
Yeah, that's an excellent point, and that's precisely what we're going to talk about in a moment. But yeah, so I mean, basically saying for finite hypothesis classes, that's it's kind of a nice framework. If you have the issue is that in real life, many times we actually have an infinite hypothesis class. So as a function, we're dealing with this uncountable in size. And so in reality, many times we actually would have here an infinity. And so that's going to be bad because then we're just having a vacuous statement here. We're saying the probability of a bad event is at most infinity, so that doesn't tell us anything. That's a problem, so we need to do something better. The union bound is very generous, and that's going to be a way where we can try to attack the problem. So for a union bound, we're kind of taking multiple events, and union bound is going to say, let's add the probability of all those events as if they were separate. But in reality, all of those events may overlap pretty significantly. And that's what we're going to try to exploit to argue and conclude that even if we have an uncountable union of events, they are overlapping in such a way that the total probability is not the sum of probabilities, but it's much less than that. And we're going to try to get rid of this infinity somehow by trying to use that. So the union bound is way too generous. It doesn't really work if you have an infinite hypothesis class.
There are charts if you need.
Oh, okay. Yeah.
Yes.
Right. Other comments? All right, so yeah, so uniform error estimation, that's kind of the name of the game to some degree at least. So what I have plotted here is in the x-axis, we can imagine that we have different hypotheses. And in the y-axis, we have the error, and we were comparing here the sample error and the actual error. What you see is just that for different hypotheses, so maybe the solid line is the actual error, and the dashed line is the sample error for some particular sample. They are not the same. And it could be that many of them are similar, and one of them happens to be big discrepancy. So in particular, you see here that for the dashed line, the minimum is attained over here. So this would be the hypothesis that minimizes the sample error. But for the actual error, these guys over here minimize the actual error. So the fact that there is this discrepancy means that minimizing the sample error will not necessarily give you the hypothesis that minimizes the actual error. Right? So you can only ensure that you're going to be close to the actual optimum if you can ensure that this gap between these two curves remains somehow bounded uniformly across all the hypotheses. All right, so but for finite hypothesis classes, in the case that this H is finite, since by the union bound and Hertz inequality we have that sample error tracks the error uniformly over the hypothesis class, we can use that to conclude that we can actually learn by minimizing the sample error. So if we minimize the sample error, we're also going to be minimizing the actual error. This is a statement. So suppose that H is a finite set of functions mapping to 0, 1, and we're gonna look at the algorithm that is defined to minimize the sample error. So it's gonna be defined such that the output of L for a sample C attains the minimum possible sample error. Then L is a learning algorithm for H with an estimation error. So rather than writing now a bound for M, I rephrase that now as a statement for E and M. Let's see. Excuse me. Here is M. With an estimation error epsilon of this sort, if we want to write it as a function of M and delta, and the sample complexity, we want to write this as M as a function of epsilon and delta of this sort. So we have here popping in the cardinality of the hypothesis class and the delta and the epsilon. So does that make sense? So with this particular value, we would be able to satisfy the conditions of the definition of learning for the algorithm being the one that minimizes the sample error. Okay, so questions about the statement? Okay, so the proof is not very complicated. Yeah, just maybe very quickly, what we're going to do here is just use this union bound and for the helping inequality. And from this one, what we can say is like, let's try to look at the right-hand side and ask, we want this to be less than epsilon. So the bad event being the fact that one of the hypotheses has a big discrepancy between sample and actual error. Then, so if we set this being equal to delta, so we can then solve for epsilon, and will give us this sort of result here. And we can basically evaluate here. So we can see that with this particular probability for every hypothesis, we have this, we can sandwich the sample error between epsilon and the actual error, and then we can use that to argue that this is also true for the best possible hypothesis, and that ends up giving us that is bounded to epsilon, and so on. We can end up concluding the result. All right, so we have a formal definition of learning, and we discussed how learning is feasible if you have a finite hypothesis set H. However, as we already heard, many of the interesting hypothesis classes are not finite, and as it turns out, it is also feasible to learn with those, provided that these hypothesis classes are not too complex. And we're going to have to discuss what that means and try to convince ourselves that that is true. And this is actually also an interesting point because there's a lot of discussion these days about having a very complicated hypothesis class where we can overfit to the training data. So we have a very rich model of hypothesis, and is this going to generalize well or not? And so what is going to be a good notion of complexity allows us to make a statement about the generalization performance of such a hypothesis class. Is there going to be simply something about the functions that can be represented within some family, or maybe are there other procedures that impact the class, the set of functions that we're representing, or the complexity? So we should examine some measure of complexity of a function class and how this determines the inherent sample complexity of the learning problem. We're going to start with a very classic notion, and then we'll continue discussing some more notions later on. Okay, how much time do you have now? Okay, no more time.